and treatment of thrombotic disorder. Already we have a very wonderful introduction by Dr. Satyak about how thrombosis is disastrous for us. Now how to treat it and how to diagnose it, because they cause heart attack, stroke and all those things. What are the, because now the buzzword is nanotechnology. Can you apply the power of nanotechnology towards treatment of thrombotic disorders? So it is an interface of two disciplines, nanotechnology and biology, okay? So I shall start with the prophetic words from Crimea. You see the year, it was way back in 1959, and he told one thing in a lecture. There is plenty of room at the bottom. Bottom means you go down and down in size. If you have a smaller, go down the size, you have a lot of space, lot of room. That means your surface area increases. Nanoparticles are extremely useful because they have great surface area. And he spoke at the time in 1959 when the nanotechnology as a discipline was not there. Nobody had perceived. The third nanoparticles came in only 10 or 15 years back. So it was a prophetic version. I start with that, and there is a session on nanotechnology also earlier in the Science Congress. Just to briefly, anything less than 100 nanometer, they come under nanomaterials. But they don't include biological materials. No protein, no DNA, nothing. No biological materials. They can be inorganic materials, metallic materials like gold, silver, etc. They can be carbon-based materials like carbon nanotubes, graphene, nanodiamond, magnetic, and so on, semiconductor like quantum dots, etc. So we have used some of these for our study in the first part, which is the diagnosis, how to diagnose a thrombotic disorder. We have used graphene. I shall show briefly how. And for the second part, we have used gold nanorods to treat, how to treat. Not to use the clopidogrel, etc. that he has told, but what are the other alternative way to dissolve a thrombus by using gold nanorods. Coming to the first part, which is a diagnostic aspect. How you will diagnose a person who can develop heart attack, who can develop stroke. So the basic premise is that the platelets, you see, there are very small cells, and they can generate still smaller particles. Platelets can generate still smaller particles, about 100 to 500 nanometer. They are known as exosomes, or they are known as microvesicles. If platelets in a person shed these small particles, previously it was known as platelet dust, like a dust. But now they have given a name. It is a very intense research area now. Now, if a person have more of platelet-derived particles in his blood, then the person can have high thrombotic risk. So that is the background. So as I told you, our blood is crowded with microparticles from different cells, not only from platelets. For example, they can be from RBC, leukocytes, endothelial cells, whatever cells are, even cancer cells. Our blood is flooded with these small particles. And also for stimulated platelets. If platelets are stimulated, they will share these microparticles. So the basic background premise is there, very simple, that we worked on. If microparticles are absent in blood, apparently healthy person, if the microparticles are present, he is liable, vulnerable to develop any serious thrombotic disorder. How to know that person has microparticles? There are certain proteins on the surface of these microparticles. They inherit some of the particles from the cell of origin. If it is for endothelial cell, they will carry something from the endothelial cell. If that is a signature peptide. If they are from platelets, they can have proteins like P-selectin or PAC1, they will be present on their surface. So you can have antibody to fish out this microparticle is original from platelets or not from platelets. Okay? And how you do this? The basic, very widely used equipment is flow cytometry. but it has its own difficulties. It's expensive. It is 1 crore rupees nearly now. It cannot be used as a bedside in a hospital all the time. Requires antibody which are to be fluorescently labeled. So what we have done that, we have used another technique which is widely used, that is electrochemical analysis, and I shall show how. In this next cartoon, basically electrochemical analysis means there is an electron flow. There is a reaction which will generate electrons. So it is an electrochemistry. Now if this electron flow is increased, conductivity is increased. If electron flow is impeded or decreased, resistance is increased, impedance is increased. So depending on the condition, you measure either conductivity or you measure impedance to say that there is some change after antibody binds. So here is a cartoon. We took the graphene sheets. Graphene is a two-dimensional nanomaterial made from carbon. You know that there is a Nobel Award given to graphene, discovered in 2010. So this is available commercially, and this is a 3-electrode system. This is the main electrode. This is the working electrode. We have already coated the electrode with the graphene sheets. Then you coat the electrode with antibody, whatever antibody. Now you see that the electrode is coated with antibody. That is background, you have to make it. Or commercially, you can ready-made antibody coated electrodes, you can fabricate. Then you take a drop of blood, and in the blood, you pellet all the platelets. Because platelets which confuse with microparticles, they have the same epitopes. You pellet all the platelets, you have what is known as platelet poor plasma, and these black dots as microparticles. So now you add the microparticles on the electrodes. Now microparticles, because they have PAC1 epitope, they will attach to electrode. Once they will attach to electrode, there is a software in the machine, and you measure either conductivity with cyclic voltammetry or impedance or resistance with Niki's plot. We have used the Niki's plot here. So next slide will make it very clear. You have the electrode, working electrode. We have the graphene oxide. Now you coat the electrode with graphene oxide layer. Then you take your antibody, and there is a blocking step. You block it, and now you are ready with your sensor. Now you put your blood here, platelet poor plasma. You don't know what microparticles are there. These green microparticles in this picture, they are derived from platelets. They have the epitopes. White microparticles, they are from other cells. Now once they are attached here, you see that green microparticles are attached, so you get a impedance signal. This slide just compares flow cytometry with Niki's plot. So in the flow cytometry, we have double color. Here one is PAC1, here is annexin 5. This right upper quadrant shows platelet-derived microparticles. If you do by flow cytometry, you see the resolution here by Niki's plot, our method. You see the strong difference once the microparticles bind. There is a strong resistance to electron flow. There is a strong resistance. We did a dose dependency. We increased the dose. It is a straight line to a certain extent. And now you take a sum of the healthy person, apparently healthy person blood, and you take 11 samples from acute myocardial infarction patient. You see that this resistance is very arbitrary, this threshold is arbitrary, but you see that in acute MI patients, these are individual cases, individuals. So most of the individuals in acute MI, their impedance is towards higher side. Interesting, you see this one. This is apparently normal, but they have higher side. The question is that whether these individuals can have some danger lurking behind. So this is a high risk group, one can find out. So in conclusion of the first part, this is a very specific sensitive method. This is most ideal for mass population screening. So you have used graphene nanomaterial for this. We have published it in 2015 in Biosensor Bioelectronics. The work is already patented. Now coming to the second part. It is a treatment. How you can treat thrombus by using gold nanorods. Okay? The basic principle, just now we have been told about the fibrinogen. In this cartoon, you see fibrinogen is something is soluble protein. It is present in everybody's blood in very large concentration. But once fibrinogen is exposed to thrombin, which is a clotting factor, you see that this fibrinogen cuts fibrinopeptides and fibrinogen is converted to fibrin. Fibrin is insoluble. Fibrin is the clot. It is insoluble. It blocks the artery, it blocks the vein. You see the next slide. Here is again the same thing. Here it is the fibrinogen and the thrombin cleavage. Once the cleavage is there, you get fibrin monomers which are soluble. These are fibrin monomers. And then immediately, spontaneously, the catch word is spontaneous, without doing anything, without enzymatic activity. These fibrin monomers attach to each other by non-covalent bonds. What's my word? Non-covalent bond. So these are the clot, nascent clot. Later on, they can be stabilized, or Dr. Jagdishwan just told that by factor 13, which will establish covalent bonds. Our target is these non-covalent bonds. If it is a non-covalent bond, with the thought, if we hit it, then this can separate. Because they are weak bonds. Non-covalent bonds are weak bonds. Can we separate? But can we give a heater inside our body? We cannot put a heater inside our body. How can we do this? We use the power of nanotechnology again. That is known as, that is a treatment way, mechanism known as photothermal therapy. You take specific materials. We took gold nanorods. We can take graphene, we can take polypyrrole, there are several materials. You irradiate it with a near-infrared laser. Near-infrared means 800 to 1100 nanometer. We have used 808 because it is a maximum effect we found. And once you irradiate it, you generate local heat. And this is not our discovery. This has been a lot of patents to cancer cells by using this method. You target gold nanorods to cancer cells by injecting it to the blood. These gold nanorods then bond to the cancer cells. Outside, you give NIR laser. So it acts as a heater, local heater. Locally it will generate heat and it will kill solid cancer cells. We use the same principle in our case. We take our sample here in the sample tube and we prepare clot from fibrinogen in vitro. It is in vitro experiment. We prepare clot and we put gold nanorods. These are the small yellow pieces are gold nanorods. We put gold nanorods in the clot. We diverted NIR laser to this and we measured the heat with a thermal camera here around. You see that there is a rarefication. These different strands, they get separated. You see the difference. How much temperature it can generate? You see, we increase the concentration of gold nanorods. It can go up to 70 degrees Celsius. It is a quite real heating effect. We did several tests to see that clot is dissolved. So I'm not going to discuss all these tests. We have used a turbidity test after 340 nanometer. We have used a fluorescently level, Alexa flow level fibrinogen we prepared and release of fibrin we measured. And we measured a drafting test with the RBC release methylene group. So different tests we did, and you see that we have documented how much percent of lysis is there. So there is nearly 20 to 30% lysis if we put heat. Okay? But these are a static condition. If there is a depolymerization of fibrin, there is a tendency to depolymerization. So there is a opposing force, depolymerization, repolymerization. Because it is a tested, static situation. But but in our body, blood is all the time flowing. So in our body, they will wash up this released fibrinogen, so it should be more effective in our blood. So we tested the same thing in a venous shear, which is 500 inverse second, and arterial shear 1500 inverse second. What we did that, we coated the cover slip with fluorescent fibrinogen, and we passed fluid over this, and we passed the fluid over this. You see that, you just see the visible, then you take a confocal microscopy, we just visualize, you see that there is a gap. Much of the fibrinogen has removed after the heating. And here also arterial shear, there is still more removal after the heating. And the released fluorescent we also measured to quantitate it. You see that in the arterial shear condition, around 50% clot will ablated, dissolved, disrupted. Okay, so it is quite good to see this, but it is an in vitro condition. It is not in vivo. So next we studied in vitro. Okay, we did also fluorescence recovery after photobleaching Prof study, confocal. I am not going to go to the detail, sorry, but this picture shows that you bleach the fibrin. This is the fluorescent fibrin. You bleach the strand, and now after some time you see this is recovered. So this shows that by heating there is a dynamism of the fibrinogen. Now coming to the in vivo condition, this picture shows that suppose it is an artery, and in the artery there is a clot. You somehow target gold nanorods to the clot. Now gold nanorods are trapped within the clot. They are targeted toward the clot. Then you give NIR laser. Now you see that after some time, this is the hypothesis. The clot is dissolved, and these fibrin strands, they are washed off. They are washed off with the flow of blood, so that there is a tremendous rarefication of clot and restoration of blood flow. So for that we took a mouse, and then we induced a thrombus by conventional method in the vein, femoral vein here by perichloride injury, and put a laser there also. Then we took the gold nanorods, we conjugated gold nanorods with anti-fibrin antibody, so that if we inject the gold nanorod, it will go and home at the thrombus site, because thrombus is composed of fibrin. If you give the gold nanorods with anti-fibrin antibody, they will go and home on the thrombus. You inject it with the tail vein, then thrombus is irradiated with laser. How can you measure that blood flow is stopped or restored? We use Doppler. I don't know Doppler, but we took a radiologist friend nearby who used this method, and you see that there are two mouse we have taken, one control, one experimental, and I don't know much about this Doppler, but you see that this pulse means that blood flow is there. These are control mouse, blood flow is there. Now we induce the thrombus formation in this mouse, mouse 1. So once the thrombus is formed, blood flow is lost. So that is pulse is lost. In second mouse also use thrombus, pulse is lost. Now in the first mouse there is no laser treatment, it is a negative control, and the second mouse is a positive control, laser treatment. You see that there is a restoration of blood flow because pulse is restored. So that shows that our method is effective in an organism, in a mouse. Next we asked one thing interesting. The normal treatment of thrombosis is streptokinase. Streptokinase is the enzyme which will clear thrombus, but it is a double-edged weapon, because it is not only kill thrombosis that side, it will affect on the fibrinogen other side also. So the danger with streptokinase is that it can cause excessive bleeding also. One way you are treating your thrombus, other way you are on the glance of doctor, because you may bleed to death. That is very dangerous. So we asked, can you reduce the dose of streptokinase, combine with photothermal therapy, so 2 modes of therapy, will it be effective? So this is the purpose of this slide. Again we took the same strategy, 2 mouse, and then first mouse, both the mouse we induced thrombus, pulse is lost. In the first mouse 1, we use very low dose, sub-therapeutic dose of streptokinase. It does not reduce the blood, it does not establish the blood flow. It is a very low dose. But once that dose combined with laser, there is a restoration of blood flow. So we can, okay, this is the same experiment we did in the sections, histology sections. It tells the same story. So there are two ways of treatment. One is standardized streptokinase therapy known as chemotherapy, now photothermal therapy. So in a nanotechnology jargon, it is known as multimodal approach. And the advantage of photothermal therapy, it is target specific. You are targeting it. It is going and sitting on the thrombus itself. And I think it has a lot of prospect, this therapy. We published last year in Nano Research, and also it is patented. I hope I am in time. So this is me. You can just match my face. This is the girl, MD student, who has done the biosensor part. And this is the boy who has done the second part. Yeah. And these are the funding agency, DST, DVT, ICMR, Tata Innovation. And finally, the Seren Bank of Ganges. Okay. Thank you.